Yeah, I think we're about ready. So over to you, Thomas.
Okay, thank you very much. Welcome everybody to our webinar. My name is Tomasz Kwiatkowski. I'm leading OWC in Poland here. And I have a pleasure to introduce the webinar of potential high voltage DC on the Polish Baltic Sea. So let us firstly introduce ourselves. The webinar has been prepared mainly by Bartosz Hunek and Piotr Jędrzejewski, who will be leading the technical part of that, and Jeff Fodiak, who is our electrical lead from the New York office, provided a vast support for that content. Now, from the oversight perspective, as you see, we have Łukasz Sikorski and myself, who did some work on the Polish side and oversighted the permitting. So, from that perspective, what is the reason of the webinar, and what is the origin of that? So, firstly, we understand that the offshore wind market is changing, and we have offshore wind farms with much higher and higher capacity, which are located much farther from the shore. On the other hand, we have also high voltage DC technology, which is actually ready for implementation, and a number of companies, which we show later on, actually started implementing this technology for offshore wind farm power evacuation. So over in Poland, what we have noticed that some of the sites have very similar conditions and features, which may provide a very valid point about high voltage DC versus AC dilemma. So we thought we'll put a presentation together with a webinar together with a white paper, which this webinar introduces. So if we can have further slide. Okay, so our webinar today is structured around these points which are presented on this slide. So we'll kick off with a very brief introduction to OWC. Then we'll move to technical elements of high voltage DC versus AC. What are the differences? And we'll describe pros and cons and cost comparison between the two technologies. So at this point, there will be quite an interesting slide presenting the difference between costs and what it actually takes, and how this can be applied to the Polish sites. This will follow by study recommendations. This is point number 4, and we'll mention also a little bit about the white paper, which this webinar introduces. And finally, we would like to welcome any questions that may rise during the presentation. So please let us know. Please put them in chat. There will be an opportunity to ask the questions. So let's start with the introduction of OWC. OWC is part of ABL Group. The ABL Group itself is a company that originated in oil and gas, and a few years ago moved to green energy. And as OWC, we provide project development, owners engineering services, and technical due diligence to clients around the world. We have over 100 staff, and the number of offices, as you see on the right-hand side. One of these offices is an office in Warsaw, presented on the map in green here. And as you see in this office, we have a number of people who actually present a broad range of skills, starting from like market analysis, regulatory elements, going to engineering, regarded like civil engineering or turbine engineering, also hydrogen elements. And we have an electrical team which will be presenting this material today. So we were working for offshore wind projects in Poland. This is the Polish flag for Wave 1 and Wave 2 projects, as you may expect. But actually, a lot of our knowledge and experience comes from working from abroad. So actually, Piotr, who will be presenting next, at the moment is working on the project in Australia. So we have an Australian flag. Bartosz is leading a project in the States, so there is an American flag. So Piotr finished his work and Bartosz hasn't started his work from the time perspective. So we can have them on this webinar here. But obviously, as you see, we have been working for developed markets like UK, Germany, and we have been working for new markets like you see Spain, Portugal, but also the Baltic states, Lithuania and Estonia. So from that perspective, on one side, we are supported by our international organization on the electrical side and on every other aspect of the services we provide, but also the team here, which is mentioned on top of the slide, is working on many projects around the world. So from electrical perspective, our services, as you can see on the slide, span from the very early analysis stage of potential electrical concept through pre-FEED, FEED, to procurement. This is what we actually do as one of the projects right now, to the support in final design of electrical solution, being it inter-array cables or power evacuation cables or offshore substations, etc. So this is what we do in terms of electrical thing. So without further ado, let's dive into the topic. So I hand over to Piotr for his part. Piotr, the floor is yours.
Thank you. Thank you for that, Tomasz. Yeah, my name is Piotr. I'm gonna give some introduction to HVDC technology, and then hand over to Bartosz for continuation of that. More details on that's what I'm about to say you may find in our white paper. But yeah, let's start. So HVDC stands for high voltage direct current, and this is an alternative technology for power transmission. Usually for most of the wind farms and most of the electrical networks around the world, we use alternating current, AC, and this is a bit more complex, especially when you need to couple it with AC-based grid. But it has many features that in certain cases may be better than AC, although usually it's also more expensive. And as I said, it uses a direct current. So in order to switch power from AC to DC, different substations design is required. There are converters at both ends of the transmission system, which also impacts the design of cables and many other implications. And the major advantage of this system is that the maximum capacity that can be transmitted with DC is not dependent on the distance, and it's constant. It depends on cable size and converter size. And it's not the case for AC, where the longer transmission, the longer cables, the smaller is the capacity that can be transmitted with them. So you may need larger cables for larger distances, or in worst case, you may need more cables, more circuits to deliver same power for a larger distance. And this is very important. This is, I think, a major feature, major reason why DC is used. and yeah, then fewer cables can be achieved with DC solution, but it comes with some costs. So as I mentioned, different design of substations, onshore and offshore, and especially offshore one is much larger compared to AC solutions, as it needs to accommodate the converter, which is really large and heavy, and it also more expensive than AC substations. And due to those reasons, the DC transmission becomes more economical than AC only at large distances. Usually, commonly considered value is around 100 kilometers. In this webinar, in our white paper, we check with cost model whether this is really 100 kilometers or maybe this moved due to changes in technology. But still, distances are quite large for economical use of a DC solution. But it doesn't stop developers to use that technology, and we see that it's becoming popular in more advanced markets in offshore wind, such as Germany and UK. Okay, so a quick technical description of the available configurations of HVDC export systems. There are two major technology types. So one is symmetric monopole and the other is bipole. First of them, symmetric monopole, is most popular. Usually was used in most applications developed so far and in many planned ones. As you see on the right hand at the top, there are one converter at each end of the system at offshore and onshore substation, and they're connected with two cables, positive and negative monopole, and these two cables together, they make up a single circuit and they cannot operate without each other. So meaning if one of them breaks, the whole system needs to be shut down, and therefore there is no redundancy in this transmission type. The other type, bipole, is a bit more advanced and not so common on the market yet, but considered for many new installations and entering the market pretty soon. It has more complex converter configuration and the third wire between the offshore and onshore substation, and it provides certain redundancy due to this third wire. This is called DMR, direct metallic return. So the two other cables are still transmitting the most of power, but in case of failure of one of them, this direct metallic return can substitute it partially, and the system is still able to provide 50% of the total capacity to the onshore substation. As I said, HVDC becomes popular in other markets, and there are three different reasons for that. First of them is that the export routes, length of the export cables is getting larger due to decline in the availability of the sites being just the closest to the shore, and also sometimes lack of possibility to connect to the grid close to the shore and necessity to go further inland. So this length of the cable, yeah, this makes use of HVDC more economical for this project. Then HVDC connection usually offers you large transmission capacity, and as the projects grow bigger, the average size of the project often exceeds 1 gigawatt, or we see some clusters of projects sharing the same transmission assets. It allows to fully utilize potential of HVDC transmission and therefore decrease LCOE for this project. And last but not least is that over the years, this technology became some more mature, and then initially when offshore wind was kicking in. Yeah, we got more experienced. We learned how to use it, and this is basically very helpful in taking decision about investing in it. And at the bottom, you may see a couple of examples from other markets where the HVDC is considered, is going to be built in a future projects. So there are some from UK. There is also one from US, which it proves that it's not only Europe which invests in this technology. And the last one is TenneT. It's very interesting because unlike the other ones, TenneT is not transmission. It's not developer, but transmission system operator. And under German and Dutch legislation, it's them who are responsible for developing offshore grid and connecting projects offshore rather than onshore. Yeah, and TenneT is world leader in HVDC connections due to that. Let's have a look at the Polish and what's happening here and where is the potential for HVDC at our Baltic Sea. So there has been 9 projects from the wave 1, but here at the table on the left we present just 2 of them, which are least advanced than others and still before CFD. And we see that both of them are actually quite suitable for HVDC export technology. And the table also presents all 11 sites from the wave 2, and many of them will have total export distance above 100 kilometers, which would also qualify them for use of HVDC technology. So this is one of the major reasons why we think that there is a big potential for HVDC in Poland. And some of these projects, especially the north ones, 60E ones, they present significant export cable distance, and they might be particularly interested in this solution. And the one more reason why we think HVDC could be applied is availability of the onshore grid connection points. Yeah, we know a lot of wind farms are going to be built, and maybe some of them will not be able to connect very close to the shore, and we need to go further inland. And with DC, that extra length will be less painful in terms of cost to developers than in case of AC technology. Okay, now I'm gonna discuss pros and cons of this HVDC, and then pass to Bartosz for cost comparison between AC and DC. And major features of HVDC technology, reasons why you may want to consider it for a project, is, as I said before, fewer cables. Then, since the single HVDC platform usually have much bigger capacity than AC, you have fewer offshore substations. And quite opposite situation happens onshore in terms of size. The onshore substations are smaller than in AC solutions. Some equipment is not necessary because converter serves quite good power quality control. So things like statcoms or harmonic filters or shunt reactors, they can be very much reduced. And these 3 reasons lead to a smaller environmental impact on the of the project, and that may simplify your permitting process and receiving environmental decisions. Then DC is usually characterized by smaller losses on the transmission than AC solutions. So the electricity delivered to the grid would be more electricity delivered to the grid, and therefore a larger profit for the project. And as I mentioned before, there's a greater flexibility and a grid connection point, and larger distances may be reached. But this is not all. HVDC has also some limitations, certain risks that you need to be aware of and mitigate them in advance. So first of them is a limited supply chain. There are at the moment three companies, three suppliers with a good track record who can deliver this solution. More of them may appear in the market, but it's a question whether they're really experienced enough and trusted to do that. And these existing suppliers, they already have a lot of requests, a lot of interest in their solutions, and there's a question whether they'll be able to supply all of that, and if that will not lead to increase in prices or lead time. I mentioned before limit redundancy. I also talked about the larger size of offshore platform and their size, therefore also its foundation. But this size implicates also smaller vessel installation vessel availability, since the same installation vessels used for AC platforms, which are much smaller, may not be capable to handle DC platform. And this fleet, which you may hire for installation, will be smaller and may also lead to some lead time increase or supply chain risk. The next limitation of HVDC technology is a timescale, and it may take up to 60 months from the decision of the procurement to actually constructing that. It's much longer than AC, where we usually consider around 36 months. And that basically tells you that you need to get involved with the suppliers much in advance to be able to purchase that and deliver that on time. And DC technology in offshore application, it's still rather new. It's been gaining some experience over the years. It's getting better and improving, but still we don't have full data about an entire life cycle of this project. We have fewer projects than AC, so there is some risk related to that. And if you would like to build broader grids of wind farms connected to each other, there's less flexibility. You can do it with HVDC. Usually with AC, you can connect as many wind farms in complex grid as you want, but here it's usually only for point-to-point solutions. Thank you. Pass over to Bartosz, who's going to talk about cost.
Okay, thanks, Piotr, for taking over. Welcome to my section about cost comparison and potential recommendations with regards to studies. So, to begin with, I must set a baseline. As it takes place in other decision-making exercises, same here, the decision between AC and DC is mainly driven by, yes, as is invariably the case, the answer is cost. Commonly, one determines there is so-called break-even point, crossing which one technology is more favorable. The main input and function parameter is distance and electrical system details. However, these bullet points here pose additional factors also which should be considered. As a matter of fact, this is a holistic project decision, not only on electrical system, isolating that one from the other parts. Coming up next, we will touch upon quantitative aspect of analysis. So Here we see warmly awaited the final part of our study. But what do I mean by that? Actually, it's a sample of our cost model tool comparing AC with DC technology, which indeed can help you making decisions. This slide contains two curves that reflect estimated cost for respectively AC and DC technology, of course, in function of total transmission distance. Both curves intersect at some point where one tech is outperforming. But what major conclusion can we draw from this analysis? So it can certainly be noticed that above around, say, 107 kilometers, seeing this chart, DC technology definitely prevails to be more cost-effective solution. Well, I also need to underline that due to some contingency and some project-specific variables, the curves representing both costs are deliberately, I underline deliberately, presented as a range of possible outcomes, so that there is no strict one so-called break-even point, but rather an area within DC tech may become more cost-effective. Well, some may ask which assumptions were taken. For DC export, we assumed 320 kilovolt symmetrical monopole, while for AC it was 220 kilovolt, having taken into account exemplary sites capacity of 1,200 megawatt. Actually, costs are understood as a capex cost in full EPCI formula for onshore and offshore substations and cables. Additionally, what is worth emphasizing and what I personally like as a takeaway, there is a significant increase in HVAC costs at around 110 kilometer transmission distance, basically, which stems from the necessity to increase the number of export cables from 4 to 5 circuits due to the capacity factor. On the other hand, some may say there is another mitigation of deploying interim compensation topside. However, it would surge costs even more significantly. So making quick recap, as you can see, this model can challenge certain signs considering AC versus DC dilemma, producing a specific and measurable outcomes. Coming up next, we will touch upon context of Polish Baltic Sea. So please move on. Well, we need to come back to homeland because we missed this context for a while. As concerns the application of HVDC systems on Polish Baltic Sea to screen specific opportunities, consideration is to be given to project capacity, total transmission distance, and potential synergies outside. Hence, there is particular focus on two Waves 1 projects, I mean Baltic 1 and Baltica 1, which might be still at a certain stage to consider DC tech. Moreover, additionally, looking at only ongoing Wave 2 seabed leasing round, standalone sites 43, 53 to 60s, potentially 44, may benefit from DC tech as well. It is worth adding that synergies are more than welcome as well. As an example, on cluster of sites 14s and mentioned while ago 60s. So coming up next, we will give some suggestions for developers. Next, and one of last parts is to discuss some potential studies which may help deciding and ramping up project progress. So basically, here's another question. What decision would developer need to make, having obtained a seabed license of site listed before? Here you see a catalog of potential recommended studies. Actually, feedback from each of them is so important to the other task you see here, so that everything should be undertaken concurrently to maximize effect of discovering your project. Everything starts from technical concept elaboration, shortlisting through technical and cost criterion, a preferred project among many, subsequently informing your project design envelope and ending with key project risks and opportunities. Coming up next, we'll answer the question, how does HVDC stand out in terms of studies? Well, HVDC schemes are quite peculiar, we need to say, as often HVDC OEMs undertake significant portion of pre-FIT or FIT studies, and particularly vast scope at detailed design stage. However, these pin down items like RFP, evaluation, supply chain, risk assessment, TNI, geotech, and structural advisory may be particularly beneficial to your position. At this moment, I would like to pass microphone back to Thomas so that he can make a summary.
Thomas, you're mute.
Sorry. So as mentioned previously, this webinar introduces the white paper, which basically presents the potential of the use of high voltage DC technology in the Polish part of Baltic Sea, as explained throughout the presentation. So you see the content of the white paper here, but basically, as presented in this webinar, it presents and shows the high voltage DC technology, its elements, pros and cons, and then applies this to the characteristics of the Polish market and especially the wave 2 sites. So the white paper will be available today, tomorrow. Please read that, please get familiar with that. If you have any questions, please ask them now or come back to us to us with the questions. We believe that this technology for some Polish sites may bring significant benefits, and as already been seen, especially on the graph and analyzed by us, some of these Polish sites will be subject to this HVDC dilemma, and some of the sites are actually on a very borderline, so a deeper analysis regarding that would be very much beneficial from what we have seen so far. So with that summary, I would welcome any questions that you may have. There may be some already in the chat itself. So I will ask Bartek to start the Q&A session. Bartek, please have a look, and we'll pick up the questions from the Q&A. Try to answer at least some of them within the time that we have.
Okay, thanks. So give me a while to sift through what we got in Q&A chat. Oh, I have one. I would like to pick up, maybe starting with Q&A. So the question is, do the presented in chart cost assumptions include steel material and substation fabrication? What are typical weights of HVDC topside? So directly having responded to this query, yes, the cost assumptions include steel material, moreover its fabrication as well. I need to say that also TNI portion and onshore civil works were included as well. As I said,
I think we lost Bartosz for a moment, so I may pick it up and answer.
predominantly hinges on.
Bartosz, you're breaking. You want to continue?
Okay. Sorry, when I stopped, at which words?
Oh, you are explaining about weights.
Okay, so weights. I dare say that it predominantly hinges on OEM design, layout and converter layout, and also I need to say that definitely on specific site and its design. So either a symmetrical monopole or bipole, and I need to say that AC part of topside as well, yeah, but kind of minor portion, but regardless. Maybe beginning with symmetrical monopole, estimated weight maybe around even 9,000 tons. However, it may reach even 14,000 tons, subject to design works that still strive to decrease the weight, and development and layout of converter system and equipment itself. Yeah, so this is for symmetrical monopole. For bipole, mainly due to doubled, for example, converter room, weights may reach even 25,000 tons, but most likely it should be lower a few thousand than this value. So hope it clarified as well. Let me investigate next queries. Okay, so another question maybe for Piotr. So Piotr, can you pick up question number 4 from our chat?
Yeah, sure. Let me find it. Okay, so the question is, do you think that HVDC will be the best technology for export for Site 60E, although it's so expensive? Okay, so maybe I'll explain it. We're going back to the cost slide as we talk about expensive cost of the project. And I think that, yes, I feel that this technology would be prevailing. It's at the moment rather gut feeling than some deep analysis, site specific with a lot of considerations, which may be different than the model that we performed here. But the projects in the area of 60E, they're all about 100 kilometers and 110 around that range, with maybe some changes due to cable routes that will happen. But as you see, the cost of AC is growing significantly around this area, and as said, applying different conditions to the model, maybe changed in capacity or something. This place where the this step of extra cable appears may shift. Still, I feel like for at least some of this project, DC would be a solution. And you're asking if this is true despite the cost of DC being so high. And I would like to highlight it that we don't go for DC for large distances because it gets cheaper there. It's rather because AC, the alternative, goes that expensive, that high, that DC becomes cheaper, but it's still expensive indeed. And the transmission costs for the projects located far away from the shore will always be will be higher, and for the projects close to the shore, close to the connection point. But yeah, to sum it up, I believe that for this projects far away, DC should be seriously considered, and I would put my bet today that at some point it's going to be developed there. Thank you.
Okay, so maybe reverse to me, and there are a lot of interesting questions. However, let's stick to a little bit more technical ones, and also there are some more general, but I will invite Tomasz to handle them. But so far, let me pick this one. Why symmetrical monopole system is limited to 1,200 megawatt? So the the answer is quick. There is no limitation at this level. Generally, the capacity, design capacities come out of converter layout, OM design converter capabilities, scalability, and also from DC cable part, so rating of it, seabed conditions, and so on and so forth. So there is no limitation at very one point. Also, the consideration is to be given to losses calculations, because converter poses an element which generates losses. Of course, both converters at both sides. Also DC cable itself. So it's important to think about converter system capacity, also including into consideration the kind of visible power rating at grid connection point, including, as I said, losses calculations. So this is the answer. And as promised, Tomasz, we see some general site-specific, also including cable corridors questions. So if you don't mind picking up them, it would be great.
Okay, thank you. So I see the question here about the cable corridor specific to Poland, and the question is actually for the closer sites 43 and 44, because we showed that there is a potential on this slide for this sites for DC. Why we think that that there is potential if they are much closer to the shore? Well, there are a couple of reasons for this. So the first reason, actually the most important one, that obviously we need to take into account when counting not the straight line distance. That's obvious. We need to count along the route. And what is important, that the cable corridors through the swoops bank, which especially for the 44 sites is obviously the closest, the closest one, is from what we see at the moment from the CPAM portal, fully booked. There is no more space in this corridor, or very little. So without that, the power from 43 and 44 especially can go through this power evacuation corridor, can be the one going through the swoops bank. So we may have to look for alternative routes, and some of these routes actually you can find on the CPAM portal. And they are very, very long routes here, which exceed 100 kilometers. So this is even more than 100, 115, 120, especially when you take into account the grid connection point that you have to go to. So this is the first reason, and the second reason is obviously the capacity, which for this sites is still quite substantial. It could be around one gig here. So definitely, when we look at our analysis and example of that, it may be good to understand really what is the route, what is the distance here. The capacity is obvious, and based on the basic calculations which we have explained here. So that's the practical reason for these sites from what I can see. So that would be the answer. Thank you.
Okay, so I see Piotr wants to pick up another question, but let me chime in by saying that I see very deep technical questions here, touching many aspects. So if you need any support or if you need to liaise with us to discuss some topics, in the white paper and also at the very end of this webinar, you will see our credentials and our mail addresses, so don't mind reaching us privately to speak to us and maybe screen some opportunities. Okay, I would like to pass microphone to Piotr.
Okay, yeah, there appeared a question again about a cost model, asking whether it considered OPEX and losses. And I would just like to clarify, as Bartosz mentioned before, it is only CapEx presented here. We do have some models for OPEX as well. We decided not to include everything into this analysis in white paper at the moment, but it would have some impact on decision of the technology for sure. We are happy to discuss it further, get some questions for you on the email addresses. And one more question, there was to name the 3 companies who can provide this solution, the HVDC systems at the moment, and I think it's not a mystery. It's Siemens Energy, Hitachi, and General Electric. These are the companies which have some track records in this offshore wind projects and HVDC transmission. Thanks.
Okay, and I see one more question which I can answer at least in general terms. The question is, do you have any comparison between AC versus DC offshore substation platform weights? Obviously we know from the market perspective we collect this information. But obviously these are like press releases and general information. We cannot present, client information as such, because they are confidential. But just looking at the market, there are obviously quite a significant differences in weights. It really depends on the capacity of the station. Probably a year ago, if I remember, there was a huge thing about a high voltage DC substation in China that basically could not be picked up by cranes in general because it weighed 22,000 tons. So from that perspective, it was basically put into place by other means, by the barge. So yes, the short answer is yes, we do, but it's case by case basis, depending on the capacity. Obviously depends if we have AC and DC on one platform, or we have 2 adjacent platforms connected by the bridge, for example, or there is some other solution. So that's the short answer to question could be quite complicated.
And adding some thoughts to it, to Thomas, what Thomas has spoken, and also what Piotr mentioned, that one of the main features of HVDC schemes in offshore wind is T&I aspect. So given the project pipeline, HVDC project pipeline, and marine operations vessels themselves, it should be analyzed at least to determine proper strategy also on geotech portion and structure, following geotech structure as well. That's why I mentioned that it might be one of the potential studies, to prepare yourself for your project in coming years, given the vast demand worldwide. So basically, also, as I said, there are many detailed questions. We may discuss them, but generally, given HVDC is nothing pre-prepared. It's maybe, I don't want to say it's novelty. Yeah, actually, this webinar and this white paper is to brisk this conversation in Poland again, because it had been brisked some time ago at the very beginning of Polish offshore wind projects. So each and every analysis is done for purpose. Everything is not prepared. It should be undertaken, analyzed, and concluded with measurable outcomes deliberately for your project. Yeah. So it also, not also, but always is deliberately done, design for specific demands. Yeah. So I see Tomasz wants to chime in.
Yeah, there is another market type question, and actually I want to, it's a long question, a part of this. And basically respond with a answer or some answer to that. The question reads that in Germany, the AC grid in the north is close to its limit, which is why our grid connection points move further south. Yeah, so it's a Germany. Cable lengths are up to 300 kilometers, but now up to 950 kilometers total due to onshore part. So what is the question is, what is the power demand in the northern part of Poland, and how likely are the long grid connections to the south of Poland? So we can only partially answer this question, because actually this question is for the Polish national grid. It's a very good question. I've actually asked that question on one of the meetings with PSE, the Polish national grid. I did not get a clear answer from that, because obviously, it needs to be, the whole system model needs to be run and understood, etc. Yeah, but there are two elements which are worth pointing out. So firstly, in the northern part of Poland is obviously much less demand than in the southern and central part, basically due to industry. It's a historical reason. But now, when we look at the northern part of Poland and we take into account the following things, that we are building at the moment and planning to build even more offshore wind farms in the north. In addition to that, there is a plan of the nuclear power station also in the northern part of Poland. So basically, from the grid perspective and system perspective, at the moment, power flows generally from south to the north. Yeah, we with all this investment what we are doing now, at least a little bit, we will be reversing that direction. So I see a potential, at least for an analysis, to understand if such long DC bridges going to the central part of Poland wouldn't be of benefit, because then this reverse action could be actually less, and maybe there would be less investments needed in the grid. But again, this is the question, very valid to be asked to PSE, the Polish Power Grid. So that's kind of, it's an interesting topic. I like it. I don't know if we have any time for another question to be answered.
I think, Tomasz, we should end. Okay, so making a recap once again, thank you very much for your presence. As I said, here you see our faces also associated with our mails. So if you have any queries to us, if you want to discuss webinars and white paper particular points, don't mind reaching out to us. And thank you very much once again for your presence, and hope speak you soon and see you later. Thank you very much.
Thank you.
Thank you. Bye.
Bye-bye.